Okay, so this slide is on the last video, so I'm not going to talk about this. All right, so the apparent weight and net force are two things that we are going to be using. The apparent weight is like what you appear to weigh. So anytime we have a problem where you are going to have, I don't know, like a graduated cylinder or something filled with water, and you're going to take something and you're going to put it into the water, and maybe you have a scale. We have those spring scales. We read the weight off of it while this thing is underwater. What we're really reading is the apparent weight. What do you appear to weigh when you're under the water? And of course, you're going to weigh less because of the buoyant force. So on land, you'd weigh F sub g, but in the water, or whatever fluid you're in, you would subtract out the buoyant force, and that's what you appear to weigh, which is much less than if you're on dry land. The other thing that we will look at, because this is no different than chapter 4 where we said, hey, what is the net force? The buoyant force acts up, F sub g acts down. So if we look at the net force, it would just be positive and then minus the F sub g because that's down and it's negative. Now, both of these things, apparent and net, are going to be 0 if the object is floating, because the buoyant force will be enough to act on the weight, and then you would have a net force of 0, you would appear to weigh 0. Okay. So we'll just look at a couple of other formulas here that are going to be useful. If we have no amount of the object above the fluid, so completely surrounded by the fluid, you can use this formula. F sub g is the weight, of course, the buoyant force. A rho, the Greek letter rho, it just means density. This is the density of the object and the density of the fluid. So we're going to take a gold medal, medallion, we're going to put it in water. And so there's a lab here that hopefully you did. And when we put it in water, it appears to weigh only 6.86 newtons, because in air, just regular old air, it weighed 7.84 newtons. So these two are the F sub g and the F sub a. So what we can basically do here is to say, all right, well, we know that apparent force is equal to F sub g minus F sub b. So we can, go that route, and we can find the buoyant force, and the buoyant force is going to be the difference between those two, so 0.98 newtons. Now, to see if it's really gold, we probably want to know the density, because the density of gold is like 19,300 kilograms. So we could use this formula of F sub g over F sub b equals the density of the object or the density of fluid water, and then we could figure out the density of the object. So F sub g is 7.84 newtons, and the F sub b we just figured out was 0.98 newtons. We don't know the density of the object, but the density of the fluid is just plain old fresh water at 1,000 kilograms per cubic meter, and I won't write those units because I'm running out of room, but make sure that you're paying a close attention to those units. We get 8,000 kilograms per cubic meter when we do that. So this cannot be gold. Maybe it's an alloy of gold or something, but gold is 19,300. So another similar question would be along the lines of, we're going to put a statue of Archimedes on a spring scale, and we see that it just weighs 460. When we went hang it in water like we did, this is the apparent in water. And then there's this unknown liquid that only gives us an apparent of this, I don't know what it is. Could be alcohol, could be oil, but it only gives us an apparent force of 380. So it's not really doing as much buoyancy as the water's doing, so it's probably not going to be, it's not going to be as dense. So what we're going to basically do is to, again, because it's completely submerged, surrounded by water, we're going to go F sub g, which is 460, over F sub b. Now that's going to be the difference between these two, right? So that'll be 110 newtons. The density of the object, we don't know what it is, but it is in fresh water, so we know the density of the fluid. The density of the object then turns out to be 4,182 kilograms per cubic meter. And then we can do it again, same formula. F sub g does not change. It is what it is in air. However, now it's going to be the difference between 460 and 380, because the buoyant force has changed. It's a different liquid. And so now our buoyant force is only going to be 80. The density of the object is 4,182, and then the density of the fluid turns out to be 727 kilograms per cubic meter. So we knew it wasn't as dense. It wasn't giving us as good a buoyant force. So it kind of makes sense. All right, this really gets to this whole idea of what does it mean to, you know, to float. That's a bad picture. There is a problem. Now that looks more like a cat than a pig, but there's a pig on a raft in one of your homework problems, which is kind of silly. But if you think about whatever we have in this raft, whatever we put on a raft, it's, if we want to call it floating, well, how much water is it displacing? Because that's going to tell us our buoyant force. So if I take 2 meters times 0.5 meters times 0.2 meters, which are the dimensions of the raft, and that's obviously as much as I'm possibly going to be able to displace. That's the most this little raft can do, is displace that much water. If I'm looking at the buoyant force, it's going to be based on the water displaced and specifically the density of the water displaced. So this is water's density right here. This is the volume of water. This is the kilograms of water displaced. So if I multiply this by 9.8, that's your buoyant force. But of course I do have to multiply by 9.8. I'm going to skip that step simply because I know you know to multiply by 9.8 to get the buoyant force. But this is floating. So this should also equal F sub g, again, if I multiply by 9.8. So I'm saying it's equal, but again, multiply by 9.8. However, I'm going to basically say, look, this is what the kilograms has, that's the most it can put on there. Being the pig, the person, coolers, whatever, that's the most. And actually the raft itself weighs 3. So really we're down to 197 kilograms of raft and person and whatever. So with your homework problem, there's a pig. Do the same process here, subtract out the pig, and that's what's left that your raft can weigh, kilogram-wise, okay? And that you can do the problem. Real quickly, this is another example I want you to really just look at and understand. I've got to displace 510 kilograms of fluid. It doesn't matter what that fluid is. So if this should go under there. If it's fresh water, then I divide by 1,000. If it's salt water, I divide by 1,025. If it's mercury, I divide by 13,600, I think it is. So there's, again, a homework problem where you're putting your ship on hectare, which is C's of mercury. Okay, well, fine. Take your kilograms, divide by whatever, like I said, 13,600 kilograms for 1 cubic meter, and that will be your volume. So that's a one-step problem. Okay, we also have a formula we can use, that should go under there, tells you the fraction immersed for floating objects. So this is different. Check your sheet. What fraction of the iceberg is underwater? Take a look. 89% is underwater. Okay. All right, so a couple of things I'm going to just quickly do here. We have an iron ball, and we're going to take that and float it in mercury, which could happen. How much of the ball's volume is immersed in the mercury? Well, we just take the volume or the density of the iron over the density of the mercury, the fluid, and we see that 58% of it is underwater, not under mercury. Okay. Now, as far as the actual weight and buoyant force, let's deal with those. We are going to need a little bit more room. Just do remember we have got 58% of it under the mercury. We kind of figured that out. Actual weight is just F sub g. So I'm going to take the weight or kilograms of volume, and I'm going to take this density, and I will get the kilograms of iron. Now, this is everything to do with F sub g. This has nothing to do with F sub b. This is F sub g. Now, we can make some connections, but this is F sub g. So I multiply by 9, and I get 3.86 newtons. Now, it turns out this is F sub g, okay, the actual weight. This is not buoyant force, although it is, because why do we know it is? It's floating in the mercury. So I went through and I found F sub g. Now, don't just assume something's going to be floating, but if it says it is, well, this is F sub b as well. Okay, now I want to show you another way to get F sub B, but that, because it's floating, I got the F sub G. It is the F sub B because it's floating. Okay, it could be sinking or rising, and then we could not make that equality. The buoyant force then, you got this, the apparent force is 0. How do you feel when you're on a raft? Do you feel pretty much like you're weightless? Okay. All right. I'm going to show you quickly another way and end up this video how I could find the buoyant force. I did find that 58% of it was under the mercury. 58% of the iron ball was submerged under the mercury. So what I'm going to do is I'm going to take this iron ball again, and I'm going to say, look, 58% of that is under the mercury. Thus, 58% of it, or that much of it, is pushing away the mercury. So this is actually going to be, I'm going to find the buoyant force another way. This is the mercury that's been displaced. Mercury's density is, every cubic meter of mercury is 13,600 kilograms. So now I'm focusing on the fluid's density. And what I'm going to find here is 0.394 kilograms. And if I multiply that by 9.8, I'm going to get the 3.86 newtons of buoyant force that I figured out previously.